For our second day of statistics, we're going to be talking about something called the normal model. So what happens in our world when we collect data and we look at it and we graph it, it often falls into what is called the normal model. If you think about the heights of adult males, after a while everyone stops growing, and what happens is there are a few people who end up short, and then most people are about average height, and then there are a few people who end up really tall. And so what we would do is graph those heights, and we would notice that the histogram of those heights would fall approximately normal, approximately symmetric, with one major cluster in the middle. This is called a normal model. You may have seen it as a bell curve before because it kind of looks like a bell, and that is the same. Sometimes we also refer to it as a normal distribution. So if you read that data is normally distributed, that means it's falling under this bell-shaped curve. Okay, well, what's so special about this normal model or this normal distribution? Well, here's what happens, and I'm going to draw another one bigger, and you'll get used to drawing these. And they don't have to be perfect, it's just to give you an idea of what's going on. When we have data that is normally distributed or falls along the normal model, the mean of the data and the median, but we really care about the mean, cuts the data in half. It is our measure of center. So 50% or half of the data is below the mean, and half of the data, or 50% of the data, is above the mean. If we're talking about a population, we would use the Greek letter mu for mean. It looks like kind of a cursive U. If we're talking about part of a population or a sample, we use x bar for the mean. That's the symbol that you see for mean on your calculator as well. Okay, so the mean cuts our data in half, and then if I take the mean and subtract one standard deviation, and take the mean and add one standard deviation, 68%, approximately, it's not exactly, 68% of our data will fall between one standard deviation of the mean, or within one standard deviation of the mean. So again, in terms of symbols, we might see the mu minus that little cursive O looking thing, that's lowercase sigma, and mu plus sigma. Or if we're talking about a sample, we would say the mean minus s for standard deviation of a sample, and mean plus s. Sometimes you'll see this referred to as zero distance from the mean. Sometimes you'll see this referred to as +1 for one standard deviation in the positive direction away from the mean, and this is -1. And we'll talk about all of those things as we go along. We're just generalizing right now. Well, what about the rest of my data? So 68%, the majority of your data in a normal distribution, falls within one standard deviation of the mean. Well, within two standard deviations of the mean is 95% of all of our data. So this is the mean minus 2 standard deviations. And this is the mean plus 2 standard deviations. Okay, so the majority of our data, 95% of our data, lies within 2 standard deviations of the mean when it's normally distributed. Now, you know, we've seen yesterday that some data is skewed, and that's not normal, and so this doesn't apply. This only applies to roughly symmetric data that falls along this normal model. Well, what about the rest of it? Well, if we go out 3 standard deviations on either side of the mean, either above or below it, that accounts for 99.7% of my data. So if you get a data value in a normal distribution that's outside of 3 standard deviations of the mean, that's very rare. That's something very interesting going on. Really, outside of 2 standard deviations is considered strange, But absolutely, if we're outside of 3 standard deviations away from our mean, we have a very unique data value or two, and we want to look at that further as statisticians. Okay, so those are general numbers. So we call this 68, 95, 99.7% rule the empirical rule. So if you read empirical rule, that's your normal model divided into those 3 segments in terms of standard deviations away from the mean. Okay, so let's do an example of this so you can understand when we might use it. Okay, so for the remainder of the lesson, we're going to use this one example and just talk about different pieces of the normal model. So we're going to talk about a nationwide test where scores are approximately normally distributed with a mean score of 70 out of 100 and a standard deviation of 10. So the first thing we want to do, anytime we read normal distribution, whether they tell you to or not, part of the work is to draw and label the distribution of scores. So as soon as you read normally distributed, you draw your normal model. So you do your best to draw that bell and start labeling it. We're told that the mean score is 70, so in the middle you put your 70, you can label it your mean, and we have a standard deviation of 10. So let's add 10 3 times. 70 plus 10 is 80, 80 plus 10 is 90, 90 plus 10 is 100. So there's the mean plus 1 standard deviation, the mean plus 2 standard deviations, and the mean plus 3 standard deviations. And then we'll want to subtract 3 standard deviations as well. So 70 minus 10 is 60. There's your mean minus 1 standard deviation. 60 minus 10 is 50. Mean minus 2 standard deviations. 50 minus 10 is 40. Your mean minus 3 standard deviations. Well, you also want to label your approximate percentages using your empirical rule. So within 1 standard deviation of the mean, approximately 68% of all my data lies. Within 2 standard deviations of the mean is approximately 95% of my data. And within 3 standard deviations of the mean is about 99.7% of my data. So that is a very well drawn and labeled distribution of scores based on the information that's given to you. And you want to draw and label this every time. Because now that we've got it labeled, we can answer some questions about it. So if we look at this model, we might be asked what percentage of scores is greater than or equal to 70? Well, 70 is my mean, so 50% or half of all of my scores are above 70, which means then that half of all of my scores are below 70. So things we want to notice: 50% of scores are greater than 70, 50% are less than 70, and some at 70. We can say greater than or equal to at this point. What percentage of scores is between 60 and 80? Well, we can say, since those are the numbers at 1 standard deviation below and above the mean, we can say that 68% of the scores were between 60 and 80. And then again, defining our empirical model, 95% of the scores are between 50 and 90, and 99.7% of the scores are between 40 and 100. Okay. Well, we can also talk a little bit more specifically about scores. So if my empirical rule between 1 standard deviation of the mean, or within 1 standard deviation of the mean, is 68%, remember this is symmetric, so each half will be 34%. So you can figure out these other pieces underneath your curve as well. If within 2 standard deviations of the mean is 95%, and within 1 is 68%, you can figure out these chunks by subtracting and dividing. So that whole width is 95%. Take out the 68% piece, subtract that out, and you get about 17%. But that's for both of these chunks, so divide that by 2, and each of those pieces would be what? About 8.5%. And you can do the same for these little pieces out there. We don't have to do it right now, but you do need to understand all those pieces. So now you can say things like 8.5% of people score between 80 and 90 on this test, or 8.5% of people score between 50 and 60, 34% score between 70 and 80, and so on. Now, sometimes also you'll be asked about half standard deviations. I don't love this. They used to do it a lot on the old exam because they gave you this normal model in the old exam and it was split up by halves. That is not done so much anymore. You aren't given this normal model, so we probably won't think too much about halves after this lesson in tomorrow's classwork. We have another way of finding different percentages. But just to expose you to that for a minute, don't believe you need to know these percentages as precisely, but on the classwork you can use this and it will help a lot. Notice that this normal model is divided into half standard deviations, and so from the mean to 1/2 of a standard deviation out, they have this as about 38.2%. We called it about 34%. If I add another 15% to each of those, now here I am 1 standard deviation above and below the mean. There's our 68%. If you add those percentages up, they're going to call it 68.2%. It really doesn't matter at this point. We have a much more precise way of finding some of these percentages in class in tomorrow's lesson. But just to practice a little bit, to prepare you and to help you understand a little bit more about this normal model, we could take that information that was given to you about these nationwide test scores, and we could ask about more specific values, like what percentage of people pass the test, say. So I'm just going to real quickly redraw the model and not label it quite so much. So here's my mean at 70, and let's say we're curious about what percentage of people scored at passing or above. So that's a 65. And one thing you want to get used to doing is what I call flagging the values we're really talking about. So in this problem we're flagging the value 65. That's what we care about. Well, if 70 is my mean and my standard deviation is 10, then 65 is minus 1/2 of a standard deviation from the mean. It's 1 standard deviation below the mean. It's halfway between 60 and 70. And we care about all these people that passed, that got above a 65. Well, what you can do then is you know that this mean cut my data value in half, so this much is 50%. And then you can look at this table for half standard deviations. And between 0 and 1/2 of a standard deviation below the mean is another 19.1%. So I could say 50% plus 19.1% is what? 50, 19.1, 69.1% of all people scored above a 65. That's it. Make sure you took some good notes, and we'll practice this a lot in class tomorrow. Have a great night.